We can use chromatography to separate out compounds, and you're going to get probably what you did in class, is beautiful separations by felt pen. We need to make sure that the end of the paper is just in the water and that you've drawn your start line in pencil. If you draw it in pen, then your start line is going to run as well, and that is going to cause you problems. We're going to put a lid on here to stop the solvent evaporating. When we want to work out RF value, we do the distance moved by the spot divided by the distance moved by the solvent. We can list the metals by how reactive they are, with the most reactive being at the top and the least reactive being at the bottom. Now you need to remember these. If you have any good mnemonics remembering these, you can pop those in the description below, in the comments below. That would really help other people. Things that are above carbon need electrolysis to be extracted, whereas things that are below carbon can just be extracted by reduction. However, things that are really unreactive, like silver, gold and copper, are generally found in the earth as their pure ores, unreacted with anything. Everything else is generally going to be reacted with oxygen in the form of metal oxides. You can also use this to predict the products from electrolysis. If the metal you are used in the electrolysis is more reactive than hydrogen, then you're going to get hydrogen as a gas. If it is less reactive, then you're going to get something else as a gas. And we can use this to predict the products for displacement reactions. If we reacted magnesium chloride with calcium, because calcium is more reactive than the magnesium, the calcium is going to take the place. So we are going to get calcium chloride plus magnesium as our products. However, if we reacted magnesium chloride with aluminium, because magnesium is more reactive, aluminium cannot take the place, it will not displace it, so no reaction is going to take place. Aluminium electrolysis is a slightly different form of electrolysis. We have one electrode up here, this is our positive anode, and another electrode down here, this is our negative cathode. The molten aluminium and the cryolite is just a compound that is added to reduce the melting point of molten aluminium oxide. It's added into this reaction vessel, and we get one reaction taking place down here and another reaction taking place at the top. At the bottom, at the negative cathode, we are going to be attracting the positive aluminium ions. They are going to be picking up electrons and turning into aluminium atoms. This is 3+, so it needs to pick up 3 electrons. And then at the top, at the carbon electrode, we are going to attract the negative oxygens. They are going to be losing electrons and turning into oxygen gas. Because we have 2 on this side, 2 oxygens on that side, we need 2 on that side, which means we now have 4 negative charges, so we need to lose 4 electrons as well. This is a carbon electrode up here, and we are starting a reaction which causes oxygen gas to be evolved. Eventually, the oxygen gas will react with the carbon electrode, and we are going to lose the electrode as carbon dioxide. So the carbon dioxide will wear away the electrode eventually, so this will need to be replaced. The molten aluminium collects at the bottom and can be taken off like that, and that is how we purify aluminium. There are lots of very important metals on Earth, and some of them are very rare. So we need to develop new ways to get rare metals out of low yield ores. Low yield is where using traditional mining methods wouldn't be financially viable. 2 of these methods are bioleaching and phytomining. Bioleaching is when we have a large body of water, say a lake, which has metal in it, such as copper dissolved in it. If we want to get the copper out of the lake, out of the water, we can add in bacteria. These will take up the copper from the water, and then they will leach out copper ions. It's basically the bacteria's way. Another method is if we have lots of copper again in the soil but at very, very low yield. So not enough for us to dig up the soil and get the copper out, say by reduction or electrolysis. We can put plants in. This is generally, believe it or not, broccoli. The plants will then absorb the copper ions from the soil. We can then cut them down and burn them, and then from the ash we can do electrolysis. The disadvantage of using phytomining is that plants grow very slowly. The Haber process produces ammonia from nitrogen and hydrogen gas. Our main source of nitrogen and hydrogen gas is getting them from the air. We can also get hydrogen gas from the electrolysis of water. They are fed into the reaction vessel where they're returned into ammonia, which is a liquid, so that can be taken off at the bottom. And any unreacted gases can go back round into the reaction. It is done at 450 degrees C at 200 atmospheres and using an iron catalyst. The production of ammonia is very important because it is an important source of nitrogen for fertilisers. The conditions used in the Haber process are actually a compromise. The forward reaction is exothermic, so this tells us, using Le Chatelier's principle of dynamic equilibrium, that we should be using a low temperature if we want to drive the forward reaction, but at a low temperature we have a low rate of reaction. So even though using the high temperature of 450 degrees drives the backwards reaction away from ammonia towards the production of the gas, the rate of reaction is so fast that it is constantly cycling between the two. So 450 degrees is a compromised temperature. The ammonia comes off as a liquid, so that can be taken off, that can be removed, which is also going to drive the forward reaction. There are less moles of product than there are moles of reactant. There are 4 over this side and 2 over this side. So high pressures of 200 atmospheres are going to drive the forward reaction because this is going to take up less space. There are less moles of it. A higher pressure would increase the rate of the forward reaction even more, but it would be dangerous because high pressure leads to risk of explosion. So 200 atmospheres is used because it is a relatively safe pressure to do it with. As we increase the pressure, the danger to the workers increases. The thickness of the walls increases, and also stuff like insurance costs are going to increase. Ammonium sulfate can be made from the reaction of ammonia and sulfuric acid, or ammonium hydroxide and sulfuric acid. Fertilisers are good because they increase crop production, but they also lead to an increase in eutrophication. When you're doing a life cycle assessment of an object, you need to look at the different stages of its life: the manufacture, the use, and the disposal, and the environmental impacts of each of these sections. So the environmental impacts of the energy, so the energy needed for production of this, bearing in mind that this generally comes from fossil fuels which have been burnt, so electricity based on fossil fuels, leading to carbon dioxide being put into the atmosphere. The materials used, whether they can be used from natural resources or whether something else can be used, whether natural resources have to be further processed, the production of the product, using the product, and disposal of the product. Using the product, does it need electricity to use it? Does anything come out of it when it's being used? Production of the product, we're talking about things like atom economy, how much of the reactants are actually going to end up in the product, how much waste is there, how much waste of the natural resources that went into it when you're making the product, and disposal of the product. Can it be recycled? Can it be incinerated for another use, or is it just going to have to go to landfill? Metals are made up of positive atoms in a sea of delocalized electrons, and these electrons being free to move is the reason that metal can conduct electricity. and why it's so good at conducting heat. An alloy looks slightly different to a metal. We still have our positive ions, we still have our delocalized electrons, but there's something else in there as well. This may be another metal it's alloyed with, or it may be something else like carbon that it's alloyed with. Pure metals have layers. Layers can slide across each other. Because they have layers and because they can slide across each other, they are soft. Alloys don't have layers, or they have distorted layers. And the distorted layers cannot slide. And because the distorted layers cannot slide, it means they are hard. For rusting to take place, we need to have iron, oxygen, and water, and that is going to result in iron oxide. You can see in my experiment here that the iron oxide is this brown, orangey red stuff that is on the sides. Rusting will actually lead to an increase in mass because you're taking the iron and you're adding in the oxygen. There are a couple of ways we can stop this from happening. We can galvanize things. We can coat things. We can use a sacrificial metal. The majority of glass we use is made up from silicon dioxide. Ceramics, such as clay ceramics, are a mixture of silicon dioxide and aluminium oxide. Thermosetting and thermosoftening polymers have very, very different properties, and this is based on their structures. Both have long polymer chains in, but thermosetting have crosslinks, whereas thermosoftening don't have crosslinks. This means upon heating, the thermosoftening polymers can just slide past each other, whereas the thermosetting polymers cannot slide past each other. Which means thermosetting polymers are going to burn and thermosoftening polymers are going to melt. A couple of key definitions you need to know. A hydrocarbon is a compound that is made up of hydrogen and carbon only and nothing else. Crude oil is a mixture of different length hydrocarbons. Alkanes are hydrocarbons with single bonds only, and the general formula for them is CnH2n plus 2. The first one with one carbon is methane, 2 carbons is ethane, 3 carbons is propane, and 4 carbons is butane. When we're drawing organic compounds, the important thing to remember is that hydrogen always makes one bond and one bond only, and carbon always makes 4 bonds and 4 bonds only. So you can see when I've drawn them, each of the hydrogens here only ever makes one bond, whereas the carbons each make 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. 1, 2, 3, 4 bonds. And because these are alkanes, they're only ever going to have single bonds. This line here represents a bond, and that is a pair of electrons. This is a covalent bond between these. You need to know the names and be able to recognise the pictures of these. And we can see the formula for these follows our general formula of CnH2n plus 2. So methane has 1 carbon and 4 hydrogens, ethane 2 carbons, 6 hydrogens, propane 3 carbons, 8 hydrogens, and butanes 4 carbons and 10 hydrogens. The complete combustion of a hydrocarbon involves lots of oxygen. That is your roaring blue flame on a Bunsen burner. This is going to be hydrocarbon plus oxygen turns into water and carbon dioxide. Incomplete combustion is where there's not enough oxygen. This is going to be your orange flame on a Bunsen burner. This is much more problematic because as well as the water and carbon dioxide, we're going to get carbon monoxide, which is highly toxic. Your white blood cells prefer it to oxygen, so you will actually suffocate to death, generally in your sleep, and carbon, which is black soot, which gets everywhere. Alkenes have a double bond and are unsaturated. The general formula of them is CnH2n. All of these are going to end in ene, so there is, with 2 carbons, ethene with 3 carbons, propene with 4 carbons, butene with 5 carbons, pentene. When we are drawing things in organic chemistry, we need to remember that hydrogen always makes 1 bond and carbon always makes 4 bonds. So ethene down here, hydrogen is making 1 bond and our carbon is making 1, 2, 3, 4 bonds. This second carbon is making 1, 2, 3, 4 bonds. A bond is a pair of electrons that are covalently shared. So a bond can be used by more than one carbon or hydrogen when we're counting things. You need to be careful looking at these ones, 1, 2, 3, 4. It would be very easy to make a mistake drawing some of the carbons in the middle here. You need to know how to name, recognise and draw the first 4 alkenes. The formulas for these: for ethene, C2H4, propane, C3H6, butene, C4H8, pentene, C5H10. You need to know how to test for alkenes. This is also the test for double bonds or unsaturation. You can see alkenes have 2 E's in there. It means they have double bonds. For this test we use bromium water and it goes from orange to colourless. Colourless is really, really important here. Clear is not going to be enough to get you the marks, it has to be colourless. To make this slightly harder, the examiners might throw in some isomers. So this double bond for butene doesn't need to be here, it could be here. And these are named differently. Here the double bond is in carbon number 1, so that is but1ene. Here the double bond is in carbon number 1, 2, so this is but2ene. Here the double bond is in carbon number 1, so this is pent1ene, whereas here the double bond is in carbon number 2, so this is pent2ene. The word mono means 1, and mer means bit, poly means lots, and mer means bits. So we can say that a monomer is 1 bit and a polymer is lots of bits that have all been put together. If we're going to have a monomer of ethene, that will just become polyethene, so just putting poly in front of the name there. And if we want to take the drawing and turn it into a polymer, we need to take this double bond and break it. So that bond goes outside, we have a single bond between our 2 carbons, that's the other half of the bond. Drawing in our hydrogens, square brackets, you need to make sure your bond extends outside the square brackets, and a little n after it, and then you need to have a big N in front of your monomer. If we want to have a polymer of propane, we're going to turn that into polypropane. We need to draw it in a slightly different way to the way you may be used to drawing it, with our double bond here and our 3rd carbon up here going round a corner. Exactly the same way, break one of the bonds, 1 bond left in the middle, other bond goes outside, and then all of the other groups around the hydrogen stay the same. Little n after it, big N in front of it. If they want to try and make this more complicated, they could change this CH3 group to a fluorine group or a bromine group. All you'd do then is exactly the same, just replace the fluorine group in the same place. Alcohols have an O H functional group, and they end in ol. So one with 1 carbon is going to be methanol, with 2 carbons, ethanol, with 3 carbons, propanol, with 4 carbons, butanol. When we draw our alcohols, we need to put our OH groups on here. And we need to remember and make sure everything has the right number of bonds. Hydrogen is only ever going to make 1 bond, carbon makes 4 bonds, and oxygen makes 2 bonds. Organic chemistry is a very likely place for them to sneak nasty questions in, and this is one of the nasty questions they could sneak in. Propan-1-ol has our alcohol group right on the end. Butan-1-ol has our alcohol group right on the ends. Propan-2-ol has it in the middle. Here is our alcohol group up here, and butan-2-ol has it in the middle here. Learn these and recognise them. Another way of producing alcohol is fermentation. This is where we take sugar, we mix it with yeast, we keep it nice and warm, and we're going to get ethanol, which you can use for alcohol, or carbon dioxide, which makes the bubbles in bread. Exactly the same process, beer making and bread making. Alcohol can be used for drinking or as a solvent. When you react it with sodium, it's going to fizz. When you react with oxygen, it's going to burn. It's just a combustion reaction. And when you react it with water, it's going to dissolve. Carboxylic acids have this as a functional group. Something with 1 carbon is methanoic acid. 2 carbons is ethanoic acid. 3 carbons, propanoic acid. 4 carbons, butanoic acid. Methanoic acid, 1 carbon making 4 bonds, double bonded to oxygen and an alcohol group. Ethanoic acid, propanoic acid and butanoic acid. You need to be able to recognise and draw these. You use carboxylic acid much more than you recognise because ethanoic acid is vinegar. It is an acid, so if you react with any carbonate, you're going to get your standard acid-carbonate reaction and it's going to fizz. And if you react with alcohols, you're going to make an ester. If you react an alcohol with carboxylic acid, you're going to get an ester. For example, if you react ethanol with ethanoic acid, you're going to get ethyl, ethanoate, and water. When we polymerise something, and this is I'm going to show you condensation polymerisation, we add monomers together. In condensation polymerisation, we're going to add these bits together here, and we're going to lose a water molecule. For condensation polymerisation, you can see we had 2 different functional groups here. The opposite ends of amino acids, which I've drawn here, and we have lost water as a small molecule. Condensation polymerisation is when we lose a small molecule from the reaction, and it is usually water, but not always. Here is the structure of DNA that I have sitting on my desk, and you can see that there are 2 lines going through it, because DNA is double helix structure. You can see each of the bases in here, all the different colours. The bases are A, T, C and G, and they go together in that format. A always bonds with T, C always bonds with G. This is to do with the number of connections they can make. So you're always going to get A bonding with T and C bonding with G. It has a sugar phosphate backbone. And there are 2 of these that go up the side around the DNA. 2 strands that can break apart down the middle when the DNA wants to replicate. A section of DNA, such as this, can be called a gene, and then genes hold the information for making amino acids and proteins, which is the building block of you and me. Sections of DNA can be read, so 3 bases of DNA can be read and turned into an amino acid. These amino acids can then build all together to make a gene. To separate out the mixture of crude oil, we need to use fractional distillation. Crude oil goes in, gets heated up until it is a gas. It then goes into a condensing column. All of the really, really long chain hydrocarbons, which don't evaporate, come off here as a residue, and we can use that, the bitumen, we can use that for making roads. It is very, very hot at the bottom, and as we move up the condensing tower, the temperature goes down. And at each different point, different length hydrocarbons are going to come off. So we have gases at the top, petrol, naphtha, kerosene, which is fuel for planes, diesel, and then fuel for boats. Short hydrocarbons are going to come off at the top, and long hydrocarbons are going to come off at the bottom. Things at the top are going to be really, really flammable. Things at the bottom aren't going to be really, really flammable. Things at the bottom are going to be really viscous, whereas things at the top aren't going to be viscous. The long hydrocarbons that come out of fractional distillation aren't always the most useful ones. We get large amounts of the long ones which aren't very useful, but we don't get very many short ones which we need because they are useful. So we can crack the long ones using heat and a catalyst. And this is going to give us short alkanes, which we want, and alkenes. Here we have a simple cell with two different metals, copper and zinc, in their own solution. So here is zinc in zinc sulfate solution and copper in copper sulfate solution. They are connected by a salt bridge or an ion bridge, and because zinc is higher in the electrochemical series, it is going to push electrons this way towards copper. A flow of electrons means we are going to have a potential difference. So the zinc is going to be giving up electrons and the copper is going to be accepting electrons. That thing that we commonly refer to as a battery is actually a cell. I know it's really annoying. A cell is one battery. A battery is more than one cells. So this is a cell, and then two or more of them together would be a battery. In non-rechargeable batteries, the chemical reaction that produces electricity, once that is used up, the battery is dead. Whereas in a rechargeable battery, there is a reversible reaction that goes on. So once the reactants are used up, you can pass electricity through it, which will cause the reaction to go in the opposite direction, recharging the battery. In a hydrogen fuel cell, we just have hydrogen gas reacting with oxygen gas and turning into water. There is a large amount of energy released. Which can be used to power an electric car. And water is the only product which means there are no carbon emissions. There are a few problems with this, predominantly with the production of hydrogen. At the moment this uses fossil fuels because hydrogen can either be made by reacting steam with coal or natural gas, which are both fossil fuels, or hydrogen is made by electrolysis of water, but that involves electricity which is generated using fossil fuels. The other problems are it's quite hard to find. The hydrogen needs to be compressed. Which is a problem because it will be explosive. It also needs a very, very large tank to store it in. And they don't work at low temperatures. At the negative electrode, we are going to have hydrogen gas minus 2 electrons turning into hydrogen ions. At the positive electrode, we are going to have these hydrogen ions reacting with the oxygen gas and some electrons, and they are then going to turn into the water. The air we breathe is made up of lots of different gases, predominantly nitrogen gas with about 20-21% oxygen in there, and then lots of other gases, including a small amount of carbon dioxide. This is very different to the early atmosphere, which is mainly formed by things coming out of volcanoes. So we had a large amount of ammonia, methane, water vapour up in the air, carbon dioxide. This would have been a pretty unpleasant place to be. Ammonia smells like, well, it's a hair dye or like really, really old baby nappies. And methane smells like farts. So the early atmosphere, the early Earth, would have smelt like farts and weak old baby nappies. The level of water vapour in the atmosphere decreased as it rained, which made the oceans. The levels of carbon dioxide decreased as the carbon dioxide dissolved in the newly formed oceans. It turned into fossils, became locked up in rocks, and photosynthesis started to take place. With the evolution of green plants, oxygen started to increase as the photosynthesis was taking place. There are three main greenhouse gases, with the biggest culprit being carbon dioxide and to a much smaller extent water vapour and methane. The bonds in carbon dioxide are really, really good at absorbing infrared or heat radiation, which traps it inside our atmosphere and warms the planet. Which means that when heat, light energy from the sun comes to us, it will be reflected back by the Earth, and normally this would go straight back out into space, but it's not. It's being trapped by the greenhouse gases, by the carbon dioxide, by the methane, which means it stays in our atmosphere, heating it up. We can see a gradual increase in the levels of carbon dioxide, which has taken up speed in recent years. And there are lots of things that humans do that have a massive amount of the levels of carbon dioxide in their atmosphere. Global warming is a slightly confusing term because not everywhere is getting hotter. While we do have places where they're getting hotter, where deserts, countries, farmland is drying out completely, and the ice poles are getting hotter as well, which is really, really bad for the polar bears. Because they live on these blocks of ice. They hunt in the water, and when they need a break from swimming and hunting, they jump onto the blocks of ice and have a rest. The problem is, if these blocks of ice are melting, there is nowhere for the polar bears to have a rest, so loads and loads of polar bears are drowning. And while the ice caps are melting, it means we are seeing increased levels of flooding in other places. As the sea levels go up, certain places, starting with places on the coast, are going to start to end up underwater. While Australia is having its hottest Christmases ever, us here in the UK are having our coldest Christmases ever, seeing unprecedented levels of snow. And the climate change doesn't just affect people, it affects animals and plants as well. As the temperature changes, the top of the mountain, which perhaps used to be under snow, is now available for habitation by new animals and plants. Now, say if you had a little house here and you knew it was protected from certain types of animals because it was too cold or too warm for them there. With a changing climate, animals are moving up and down slopes, their habitats are changing as the temperature changes and as the location of their food source changes. Your carbon footprint is how much carbon your daily activities contribute to the atmosphere. This is going to be impacted by things such as whether you decide to drive or whether you walk to your location, and whether you decide to eat food that is grown locally or food that has had to travel a long distance. Lots of human activities contribute to the production of carbon dioxide. Burning fossil fuels for use as electricity, deforestation, cutting down trees so that the trees can't take up carbon dioxide from the atmosphere anymore, and our reliance on petrol cars. The predictions for the levels of carbon dioxide in the atmosphere is that they are just going to increase, and global warming is going to increase as well, unless we as a population decide to do something about it. One of the major pollutants is sulfur dioxide. When this goes up into the atmosphere, dissolves in the clouds, it is going to come back down as acid rain. This is going to have effect on a wide range of things. It is going to hurt the animals that come into contact with it if a lake or an ocean or a pond becomes too acidic. That's going to start to kill the fish and the plants in there. Plants are not going to appreciate having acid rained on them, so they're going to die, and it is also going to destroy limestone statues, which are going to dissolve in the acid rain. Too much carbon in the air is going to lead to large levels of smog and global dimming. This is particularly prevalent in developing countries. When I was in Beijing, it was really hard to see out the window because it was so smoggy. Water vapour is going to contribute to the warming of the planet. Carbon monoxide is a toxic gas, and nitrogen oxides are going to contribute to both smog and acid rain. We would not survive very long without water. But only a small percent of the water on Earth is suitable for us to drink, so we need to remove salts from it, which is desalination, and we need to make it safe to drink, or potable water. To make water safe to drink, we need to remove any dirt, mud in there, so any large solids. We need to remove the bacteria, and we need to remove any nasty or unwanted bits of too many mineral ions, like the salt that would be in seawater. We add in various different things to water. We add in chlorine to kill things, and we add in fluoride for tooth protection and bone protection.